Welcome to the second part of thermal properties of matter. In this part, you will learn about types of thermal expansion. Types of thermal expansion. Linear expansion when there is expansion in length. Areal expansion when there is expansion in area. And volume expansion when the expansion is in volume. Let's study these expansions in detail. Linear expansion. When a substance in the form of wire or rod is heated, its length increases, and this is known as linear expansion. As shown in the diagram, at any temperature θ1, the length was L1, and when the temperature is increased to θ2, now the length will be L2, and this one is the linear expansion of the rod. Let us consider a rod of length L1 at θ1 degree Celsius temperature, and if we increase the temperature of the rod by heating to θ2 degree Celsius, it will expand. And let L2 be the length of the rod at θ2 degree Celsius. Therefore, the increase in the length will be L2 minus L1, and that is denoted by delta L. Experimentally, it is proved that change in length is found to be directly proportional to original length of the body, that was L1 in this case, directly proportional to increase in temperature, and that is θ2 minus θ1 in this case. So by combining the two equations, you will get delta L, the change in length, is equals to alpha, the directly proportional constant, and is known as coefficient of linear expansion, into L1 into θ2 minus θ1. So from this equation, you can calculate the value of alpha, and that will be equal to delta L divided by L1 into θ2 minus θ1. Now, if L1 is 1 and θ2 minus θ1 is 1, then alpha will be equals to delta L. Hence, you can say that the coefficient of linear expansion is the change in length per unit original length per unit change in temperature. Now, the final length will be L1 plus delta L. That means L1 plus L1 into alpha into θ2 minus θ1. I have put the value of delta L from this equation to here in the final length. Now from this equation you can take L1 common. So you will get L1 into 1 plus alpha into θ2 minus θ1. And which is the equation for the final length of the rod after change in temperature. On the similar basis, superficial expansion. When a body is heated, the area of the body increases, and it is known as superficial expansion. As shown in the diagram, there is an area A1 at any temperature θ1, and now the temperature is increased to θ2, and the area after expansion is A2. So the change in area will be A2 minus A1. Again, experimentally, it is found that the change in area is directly proportional to original area, directly proportional to change in temperature, and when you will combine these two, you will get delta A is directly proportional to A1 into θ2 minus θ1. And when you will remove the directly sign, there will be a constant, and now this constant is beta. So beta will be equals to delta A divided by A1 into theta 2 minus theta 1. Again, if A1 is 1, theta 2 minus theta 1 is 1, then beta will be equals to delta A. That means the coefficient of superficial expansion is a change in area per unit original area per unit change in temperature. Again, the final area will be A2, and that will be equals to A1 plus change in area delta A. By putting the value of delta A, you will get A1 plus A1 into beta into theta 2 minus theta 1. By taking A1 common, you will get 1 plus beta into theta 2 minus theta 1. And that is the equation for final area of metal sheet after changing temperature. Cubical expansion. Here, volume V1 is the volume of this cube at any temperature theta 1, and the volume at temperature theta 2 is V2. When a body is heated and the volume of the body increases, then it is a cubical expansion. And the increase in the volume delta V will be equals to V2 minus V1. And experimentally, it is observed that the change in volume is directly proportional to original volume and directly proportional to change in temperature. So the delta V will be equals to gamma into theta 2 minus theta 1 into V1. Delta V equals to gamma into theta 2 minus theta 1 into V1, where gamma is a coefficient of cubical expansion. And if V1 is 1, theta 2 minus theta 1 is 1, then gamma will be equals to delta V, means the coefficient of cubical expansion is the change in volume per unit original volume per unit change in temperature. Now, final volume V2 will be equals to V1 plus change in volume delta V. By putting the value of delta V, you will get V1 plus V1 into gamma theta 2 minus theta 1. By taking V1 common, you will get the final volume after the change in temperature. The graph represents the coefficient of volume expansion of copper as a function of temperature. You can see that the coefficient of volume expansion is changing linearly, and then it varies non-linearly at higher temperatures, and then it becomes constant.